So the first of our mathematics learning goals for our course is to build connections between the arithmetic of how we work with complex numbers on the one hand, and the geometry and visualization of what those operations look like when viewed in the complex plane on the other hand. So this is what I hope is a perfect example of what Klein calls the Plan B philosophy of learning mathematics, that we're learning kind of both an arithmetic and also a geometric perspective on the same thing at the same time, really emphasizing the connections between the two and how to see an algebraic operation as geometric and how to take geometric intuition and let it help us to interpret what's going on with the arithmetic. So what does that end up looking like in practice? We want to connect the symbolic representations of and arithmetic operations on complex numbers with geometric operations in what we call the complex plane. So let's review the important definitions and some things to know about what we're working on. So first of all, when I say complex number, what do I mean? The story of complex numbers begins with what's called the imaginary unit. The imaginary unit is a symbol that we call I that has the property that when I multiply it by itself, the result is the real number -1. So this is the characteristic property of what I is, and what it means is that it is a number which, when squared, gives us -1. Now, a couple of things that are important to notice about this. The first is that I'm avoiding, very carefully and strategically, using the word square root right here. And hopefully some of the reasons behind that will become clear as we move forward. But also, I think it's important to realize that particularly if we teach about imaginary and complex numbers with our students coming up through middle and high school, this is a major paradigm shift. This is a moment at which a lot of their intuitions about how multiplication works get upended. Because after all, students are very well conditioned into the idea that if I multiply any number by itself, the result is going to be a non-negative real number, right? Negative times negative is positive. There's no way to get a negative when I multiply two numbers of the same sign together. And a lot of those intuitions are just not going to serve them once we start working with imaginary numbers. So it's important whenever these sorts of paradigm shifts happen to be very careful with language. Because it is still true that for real numbers, a square is never non-negative. And so if we're careful to always use words, qualifiers like real, when we talk about this with students, that can help them to put the new information and the new surprising properties of complex numbers into their own category and still be able to hold on to their intuition that was previously all-encompassing, but which now they have to put into a new, smaller box called this works for real numbers, but I might not be able to rely on this for complex numbers. So carefully bracket students' intuition when you're introducing imaginary and complex numbers. So when I say the word imaginary, what I mean is a number which is a real multiple of the imaginary unit I. So 3i, 10i, -πi, those would be what we call purely imaginary numbers. And so when I take an imaginary number and a real number and I add them together, which doesn't feel like something that makes any sense when we first think about it, and it shouldn't, but if I can do that formally, if I add together an imaginary number, a real multiple of I, with a real number, the result is going to be something we call a complex number. So a plus bi, where a and b are real numbers, formally speaking, that expression defines a complex number. We say that a is the real part of that number and that b is the imaginary part of that number. And it's worth noting that the real part and the imaginary part of a complex number are both real themselves, right? So the imaginary part of 3 plus 6i would be 6, the real number 6, not 6i. So that's what complex numbers are. We use a blackboard bolded C to denote the set of all complex numbers. And typically, when we're writing an arbitrary complex number or a variable, we tend to prefer, instead of using X, as we always did for real numbers, the tradition is to use Z instead. Just to kind of remind ourselves that this unknown quantity is not, by assumption, standing in for something that's necessarily real. We might be thinking about that unknown quantity as something that's complex. So a couple of things to note. And I'm going to take these out of order. So the first is that how does it even make sense to talk about adding together a real number with an imaginary number, given that those two things don't even a priori reside within the same mathematical system? How do we make sense of that expression in the first place? Well, one way that mathematicians square this circle is that they construct the complex numbers in such a way that they sort of suspend their disbelief about I. We end up doing a lot of that, I think, intuitionally. And they declare that I is an indeterminate. They sort of put it on the same footing as we would put an unknown variable like x, right? And so what happens in that viewpoint is that they can do arithmetic with indeterminate multiples of indeterminate quantities, because that's just polynomial arithmetic. We know how to multiply, for example, 2 plus 3x multiplied by 1 minus x. That's something that we have built an entire infrastructure around doing polynomial operations with. And then after the fact, if we remember the fact that this symbol I has the property that I squared is equal to -1, it allows us to carry out further simplifications on our answer. So that multiplying 2 plus 3i by 1 minus I looks just like multiplying 2 plus 3x by 1 minus x, because we know how to multiply polynomials. The difference with the i's is that in the end we can remember that when I have this I squared, I can replace it by -1 and simplify my answer into a real number plus some real multiple of I. So this is the game that mathematicians can play epistemically to kind of get the complex numbers in a rigorous fashion. Right? We treat them just like they're polynomials, except that at the end of the day, we remember that I squared is equal to -1, which permits us also to rewrite I to the 3rd power, I to the 4th power, I to the 10th power, and so forth, just using the property that as soon as I've multiplied I by itself a single time, we end up simplifying that to -1. And so if we're feeling fancy, as people who study algebra often are, they write the complex numbers are the set of real coefficient polynomials in a variable called x, where we remember at the end of the day that x squared plus 1 is equal to 0. In other words, x squared is equal to -1, where the role of x here is really just a code word for I. So that's a sort of an epistemic issue that we might have in the beginning of defining where complex numbers come from. Why should it even make sense to add an imaginary and a real? Well, we treat them just like adding monomials with a variable and constants, right? And so we get polynomial arithmetic showing us the way. Now, what about that geometric connection? How do we make the idea of complex numbers into something that we can visualize? Well, the connection is that because a and b that define the complex number a plus bi, because those are both real numbers, we can also treat it like it's an ordered pair, where the real part is in the first coordinate of the ordered pair and the imaginary part is in the second coordinate of the ordered pair. And therefore, a complex number a plus bi and a vector a comma b inside of the xy plane have an awful lot in common. So we're going to end up using the xy plane as a way to visualize complex numbers, treating the point that has coordinates ab as being equivalent in some ways to the complex number a plus bi. Metaphorically, we think of them as the same thing. But as we go forward with this viewpoint, it may be worth thinking occasionally, well, how much of what we're doing here is exactly the same as what we would have done with vectors in linear algebra, and how much of it is new? Right? Because it turns out that as soon as we're working with complex numbers instead of vectors in the xy plane, we end up getting more arithmetic than we bargained for. After all, in linear algebra, the only operations we're guaranteed to be able to do with vectors are addition and scalar multiplication. So we can multiply vectors by scalars. But as we've already seen in this video, we can multiply a complex number by another complex number, and that's not something that we can do with vectors in general. So complex numbers are a richer source of arithmetic than vectors in the xy plane are. And yet, being able to visualize complex numbers as vectors in the xy plane is going to give us a really, really rich source of mathematical, geometrical, and algebraic intuition this semester. So what we get in the complex plane is a lot more than we bargained for. Let's take a look at what that looks like. So welcome to the first time for our course to the complex plane. Sometimes it's also called the Argand plane for a mathematician who kind of first sort of popularized this idea. So in the complex plane, we have complex numbers like 2 plus 1i that are visualized just like the point with ordered pair coordinates 2, 1. Right? So all that does is just gives us a different perspective on what complex numbers are and how we can interpret points in the xy plane. A couple of shifts in terminology. Instead of calling this horizontal axis the x-axis, as we would in the xy plane, we call it the real axis, Because on the real axis is where numbers that have no zero imaginary part live, like the number 3.5. It lives on the real axis because it's a real number, because that imaginary part 0 means that 0 times I makes the imaginary part float away. And so we don't have to imagine that it's a complex number anymore. We can just treat it as though it's real. So we call the horizontal axis the real axis for that reason. Meanwhile, the vertical axis would have a number like 6i on it. And so because that number has no real part, it has a 0 real part, we might call that a purely imaginary number. And so we call the vertical axis in the complex plane the imaginary axis for that reason. So all we're doing so far, right, is just replacing our ordered pair framing of what points in the xy plane represent with just complex number real and imaginary part framing. Right? So we have all 4 quadrants at our disposal because we can have both positive and negative real parts, positive and negative imaginary parts, and so on and so forth. So this is what the complex plane fundamentally is. And a lot of the action for us this semester is going to happen right here. So in our next video, we want to take a look at what are some other perspectives for how to represent complex numbers using the complex plane. So far, we've been using what we might call rectangular coordinates, right? An x-coordinate and a y-coordinate. But there is a second perspective that ends up being really, really helpful when we start thinking about arithmetic of complex numbers that we'll take a look at in the next video.